Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying Matrices and Determinants lecture 3. So we had taken a pause from this lecture series on YouTube because of the revision series and now that thing is quite sorted as of now. So I'm continuing with this this lecture series and treat this entire remaining series as the revision series only because there are few subtopics which are really important in matrices, determinants, permutations, probability and conics. So we'll be covering them in next 10 to 15 days, approximately max to max 10 to 15 days. Won't be taking more than that, but treat these remaining lectures as the revision lectures only. Okay. So let us first talk about symmetric and skew symmetric matrices. And the condition is if A transpose equals to A, then A is symmetric. If A transpose equals to minus A, then A is skew symmetric. So we talked about A transpose in the previous lectures, right? And let's take one example for the symmetric matrix. And before moving with the example, let's declare that these all are for square matrices. Whatever we are defining over here, these are all are for square matrices. So let's see, let's take the diagonal elements as A, B, C and these elements as 1, 2, 3 and 1, 2, 3. Now this is how a symmetric matrix looks like. If I try to find out the A transpose or A dash, whatever you call it, then with the help of our understanding of finding out the transpose with the help of matrix A, this row would become this column, that would be A1, 2. This row would become this column, that would be 1B, 3. And this row would become this column, that would be 2, 3, C, right? Now I can clearly see that this and this are same. A1, 2, 1B, 3, 2, 3, C, right? So both of them are same. So in such a case, these matrices are called as symmetric matrices, okay? Now, in case of skew symmetric matrix, you will get a minus sign over there. Now, important thing in case of skew symmetric is these elements have to be zero. Why? Because let's say if this is a skew symmetric matrix, then these elements would be negative. And if I write the A transpose, then these elements would become negative. So in reality, both of them are not negative of each other because these elements are not going to be zero. These are elements are not changing the sign over here. So if this has to be negative of this one, then this would have been like this, right? This should have taken a negative sign over here. But in that case, this matrix would entirely change. This won't remain the A transpose of this matrix, right? So it would become the negative of this one, but it won't remain the transpose of this one. So the only solution to that is make all the diagonal elements as zero. If diagonal elements in both of them are zero, in that case A transpose equals to minus A. This holds true and it also stays transpose, it also becomes a negative one, right? So this is a very important condition for skew symmetric matrices. Now let's talk about certain theorems and properties. For any square matrix A with real number entries, A plus A dash is a symmetric matrix and A minus A dash is a skew symmetric matrix. Let's look at this with an example. Let's say we have this matrix B called A plus A dash, right? If I want to find out B dash, we're getting A plus A dash dash, right? And we know that dash goes inside, that would become A dash plus A dash dash, right? Now this becomes A dash plus this is nothing but A transpose transpose, so that becomes A with the Hilbert property. So this and this are is same actually. So B equals to B transpose, right? And similarly, if we have, let's say C equals to A minus A transpose. If I find out C transpose, I'll be getting A minus A transpose transpose. That would become A transpose minus A transpose transpose, right? So this would become A transpose minus A. So this is minus times A minus A transpose. So basically C equals to minus C transpose. Okay. So this becomes the skew symmetric, this becomes the symmetric, right? Now if I talk about this property, any square matrix can be expressed as the sum of a symmetric and a skew symmetric matrix. What do we mean by that? So let's say I have this matrix A and I write it like 2A by 2, right? And what I'll do now, I'll split this matrix like this, A by 2 and A by 2. I'll add A dash by 2 over here and I'll subtract A dash by 2 over here, right? So this becomes A plus A dash by 2 plus A minus A dash by 2. And we just prove that this matrix is symmetric matrix and this matrix is skew symmetric matrix. this property is as good as the property which we studied in functions, that a function can be represented as a summation of odd function and even function. So this is more or less like the same, right? So the last property is if A is a symmetric matrix, then minus A k times A transpose A raised power n A raised power minus 1, no, not minus 1, A inverse B raised power B transpose A B are also symmetric matrices. So let's take an example of this one. This looks very complicated. So we have B transpose AB. So let's say we have this matrix C called B dash AB, right? And it's given that A is a symmetric matrix. So A equals to A dash. This has been given. Okay. So I'll try to find out C dash. That would be B dash AB dash, right? Now, in case of in case of product, when we take the dash, the order changes, right? So that would become B dash, A dash, and B dash dash, right? So reverse order. Okay. Now B dash would stay the same. A dash is A only, and B dash dash is basically B only. So this becomes this only. So C equals to C dash, right? So that means if A is a symmetric matrix, then this would also be a symmetric matrix. You don't really have to remember these properties, but have the idea of the proofs, so that because you'll be using these steps in actual questions. It's not just about the proving part. You'll be using these steps in the actual questions. So you can prove this for other properties too. I'll try to prove this property as well, A raised power n. Okay. So it's not like you just have to remember these properties. You have to also understand the proofs so that you can use these steps in the actual questions. So we have the matrix B equals to A raised power n, right? Now I want to find out B transpose. So that would be A dot A dot A dot A dot till A n times, right? This is n times, and transpose of this matrix. Now yeah, over here this comes first, then this comes second, and this comes last, this comes second last, right? Reverse order. That would be A dash dot A. Doesn't matter in case of these identical matrices, but still A dash A dash dot A dash dot A dash till A dash. Okay. So you can see that this becomes A dash raised power n. So what do we mean by this? We actually did A raised power n transpose, and that became A transpose raised power n. Basically, this dash can come inside and this power can go outside. So when from now onwards, whenever we see this kind of thing, we'll directly write it as A dash raised power n. Okay. So yeah, you can also do similar kind of activity for other properties, other matrices as well. Okay. Now let's look at few more properties and theorems. A is a skew symmetric matrix. Now we are talking about skew symmetric matrix. Then A raised power 2n is a symmetric matrix. Okay. So we have this matrix where A dash equals to minus A, because it's a skew symmetric matrix. Now we have to find out the dash of A raised power 2n dash. Okay. Now with the help of the previous property which we studied, we can take dash inside and take the power above it. So this would become A dash is actually minus A raised power 2n. So minus 1 minus A is nothing but minus 1 into A. Minus 1 is a scalar. I can take that outside. If I take that outside, that would become positive because the power is even over here. So that would become A raised power 2n only, right? You can clearly see that this became this only. So it's a symmetric matrix. For a skew symmetric matrix having a power, even power, it would become a symmetric matrix. And for obviously odd power, it would become a skew symmetric matrix, right? Now, these properties are more or less same, which we derive for symmetric matrices. You can do it for yourself. Now let's look at this one. If A, B are two symmetric matrix, then A plus minus B, AB plus B are also symmetric matrix, and all these conditions. Okay, let's try to prove this one. So we have A dash equals to A and B dash equals to B. We are not doing anything. We are just applying the simple properties, which we studied in previous lectures. Okay. So we have C matrix called AB plus BA. Now we want to find out C dash. That would be AB plus BA dash, right? Now dash can go inside. That would become AB dash plus BA dash, right? So in this case, order would reverse. That would become B dash A dash plus A dash B dash, right? So B dash A dash is nothing but B dot A because B dash is B, A dash is A, plus AB. Now this is same as this only, just the reverse order, AB plus BA, right? So in case these two are symmetric matrices, in that case AB plus BA is also a symmetric matrix. Okay. Now let's look at one example. If P is a 3 cross 3 matrix such that P transpose equals to 2P plus I, this is I actually, where P transpose is the transpose of P and I is the 3 cross 3 identity matrix, then there exists a column matrix X, X, Y, Z not equals to 0, 0, 0, such that these are the options. Okay. Now, how should I proceed in this one? Because there is no hidden clue over here. So when we don't have a kind of any kind of clue, what we'll do, we'll just transpose it, because that's what the question is all about, transpose, right? So P dash equals to 2P plus I is given. I'll take the transpose once again. I'll be getting P transpose equals to 2P transpose plus I transpose. Now 2P transpose scalar can come out. That would become 2 times P transpose plus I transpose is nothing but I, and this would become P. Now what I can do, in options I cannot see P transpose, so I'll use this over here and eliminate the P transpose. Be getting P equals to 2 times 2P plus I, right? So this would become 4P plus 2I plus I, that would become 3I. P equals to. Now I'll be getting 3P equals to minus 3I. 3 gets cancelled. P not yeah, P equals to minus I. Now we have been given one matrix X in the options and also in the question. So we'll post multiply it, because in the options we have post multiplication. So I'll multiply over here, and that would become minus I times X, right? So anything multiplied with identity, that would become minus X only, right? So Px equals to minus X. So D is the correct answer. Now let's solve this question. If P equals to this matrix and A equals to this matrix and Q equals to this expression and X equals to this expression, then the value of X is equals to. Now in these kind of questions, you don't get a clue in the first instance, but when you start writing this particular expansion, or this, if you start expanding this particular expression, then you will get a clue what you have to do. Now I try what I'll do, I'll try to write this in a detailed form, in an expanded form. So that would become P dash dot, if I replace Q with P dash, that would become P dot A dot P dash. Then again I can write it like P dot A dot P dash. I can do this for 2005 times, right, until the end. P dot A dot P dash and multiplied by P, not A, P. Okay. So now we know that in any kind of product series, we know that we have to reduce it to some simpler form, right? Be it a tan series or a chord series, be it an algebraic series in progressions. In case of multiplication, what we do, we try to merge two elements or two members of the particular series, and then reduce it to a singular form. Then again use that singular form to merge it with the other element, and reduce the entire product series into some simpler form, right? So that thought process would let me think that P, let me try out multiplying P dash dot P. So if you try to multiply P dash dot P, that would come out to be I. That is identity matrix. Now basically this expression, this is I, this is A, so IA is nothing but A only. So this expression converts to A, right? Now again this particular expression would convert to A. Similarly this expression would convert to A till the end, right? So here it would convert to A. So basically you can see that we have 2005 times these brackets, and we are getting 2005 A's. That would become A raised by 2005, and this P dash P, that would become I. So multiplied by I, that is only A raised by 2005 only. Okay. Now again, when you look at these kind of powers, it's kind of obvious that it has to be reducible in certain form, right? So basically I'll try to find out the value of A square. So that is 0, 1, 0, 1 multiplied by 0, 1, 0, 1. If I do the multiplication, I'll be getting not 0, this is 1 over here. I'll be getting 1 over here, I'll be getting 2 over here, I'll be getting 0 over here, and I'll be getting 1 over here. So if I try to multiply it once again, I'll be getting 1, 2, 0, 1 and 1, 1, 0, 1. Now I'll be getting 1 over here, I'll be getting 3 over here, I'll be getting 0 over here, you'll be getting 1 over here. So you can see that this is the value of a cube. Now you can see that the remaining portion is same, only this number is changing, this number is changing. So obviously because of this pattern, a raised power 2005 would become this a option. Okay. So these kind of questions can be asked. It's quite difficult for PGDB to ask these kind of questions, but the main thing is the thought process, how to reduce these kind of product series. It's a mathematical format. It's not just limited to matrices. Whenever you see a product series, you tend to merge two numbers or two elements of that series to a simpler format, right? So that one concept is being used over there. Regardless, it's a matrix question. Now when we don't have any clue, we tend to write down what has been asked, and that is going to give us the clue. Okay, this p dot p dash equals to I, and basically p is an orthogonal matrix. So these kind of patterns you have to observe in the actual questions, and matrices is a little, counterintuitive in such terms. You don't really use it on a day-to-day basis, so that becomes a little counterintuitive. So these kind of clues and these kind of thought process would really help you in solving the problems of matrices. So today's lecture was still here only, and in next lecture we'll be talking about determinants and the properties of determinants. So let's meet tomorrow. Thanks for watching.